When we speak of physics, we are not simply discussing numbers on a page. We are speaking of the universe itself, of the hidden rhythms that guide the stars, the galaxies, and even the fragile thread of life. Physics is the poetry of existence, a language that explains why anything exists at all. For many people, these mysteries pass unnoticed. But for Michio Kaku, they became an irresistible calling. He was only 8 years old when the newspapers announced that Albert Einstein had died. The reports described something haunting. On Einstein's desk lay an unfinished manuscript, his final, greatest work. Even as a child, Kaku was struck by the mystery. What question could be so vast that even Einstein himself could not complete it? That manuscript was Einstein's attempt to create a single equation, perhaps no more than 1 inch long, that would unify all the forces of nature. An equation that, as Einstein once said, would allow us to read the mind of God. The idea was overwhelming. Here was not just science, but a dream that touched the deepest corners of human imagination. Kaku rushed to the library, eager to learn who Einstein was and what secrets his work contained. He discovered relativity, the astonishing truth that space and time are not rigid, but flexible, bending around stars and planets. He learned that gravity itself is the warping of the cosmic fabric. And he discovered Einstein's unfinished quest, the dream of a theory of everything. For young Michio, this was not just knowledge, it was a calling. If such an equation existed, he wanted to help find it. That childhood moment became the compass of his life. Decades later, Kaku would help develop string field theory, one of the central branches of string theory, which proposes that the universe is not built from particles, but from tiny vibrating strings. Each vibration corresponds to a particle: electrons, quarks, photons. In this view, the universe is not a cold machine. It is a symphony, and the laws of physics are its harmonies. Yet beauty alone was not enough. The mathematics of string theory proved unimaginably complex. Even the fastest supercomputers strained to handle its equations. The dream of a 1-inch formula seemed locked away by the sheer weight of calculation. Then came a new possibility: quantum computers. Unlike ordinary machines that process zeros and ones step by step, quantum computers exploit the strange rules of quantum physics. An electron can exist in 2 places at once. A photon can spin in opposite directions simultaneously. To us, it sounds impossible, but in nature, it happens every moment. When this principle is applied to computing, the results are extraordinary. A traditional computer explores a maze one turn at a time. A quantum computer evaluates every path at once. Problems that would take centuries to solve could be unraveled in moments. For Kaku, this is more than technology. It is hope. He believes that quantum computers may finally provide the power needed to test string theory, to simulate the grand equations of nature, and perhaps to complete the dream Einstein left unfinished. It is striking to imagine how a single newspaper headline shaped an entire life. A boy who once wondered about an unfinished book grew into a physicist, standing at the frontier of that very mystery. His work continues the echo of Einstein's last quest. And so the question remains: will humanity one day find the equation that unites all the forces of nature? Will we uncover a formula that explains galaxies, black holes, time itself, and the essence of life? Perhaps the answer will not come from paper alone, but from machines that think in ways we cannot. Computers that operate in parallel realities, where infinite possibilities coexist. For now, the search continues, somewhere between imagination and mathematics, between curiosity and cosmic truth. The dream of Einstein still waits to be fulfilled. Every revolution in human history has been fueled by new tools of thought. The abacus gave merchants the ability to count. Mechanical calculators transformed trade and navigation. Digital computers reshaped the entire modern world. And now, according to Michio Kaku, we stand at the threshold of another leap. A leap so great that digital computers, the very machines that built our age, may one day look primitive, like relics of another era. This leap is the age of quantum computing. It is not an incremental step forward, but a reimagining of what it means to calculate, to solve, to think. If digital machines gave us the information age, quantum machines will reshape medicine, energy, security, and perhaps even the future of civilization itself. To understand why, one must see the limits of the technology we rely on today. For decades, computer power doubled roughly every 18 months, a rhythm known as Moore's Law. Each year, processors became smaller, faster, more efficient. The world adapted to this cycle. Economies, industries, and expectations grew around the assumption that technology would continue to accelerate. But the law is breaking down. Transistors, the switches that form the backbone of digital circuits, are now only a few atoms across. At such a scale, quantum mechanics itself intrudes. Electrons no longer behave like neat, reliable marbles rolling along a track. They blur, tunnel, and leak. Circuits short out. The exponential climb of Moore's Law begins to flatten. And with it, the promise of endless digital growth comes to an end. Physicists warned of this decades ago. But now the warning is reality. We cannot shrink transistors forever. The digital world is reaching its natural boundary. And so, a new path must be taken. Not smaller transistors, but an entirely new foundation. Machines that compute with the strange rules of atoms themselves. That is the promise of quantum computing. Instead of bits, which are locked into 0 or 1, quantum computers use qubits. A qubit is not just 0 or 1, but all the states in between, existing simultaneously. To many, this seems absurd. How can something be two things at once? Yet this is the essence of quantum physics. Electrons, photons, and atoms do not obey the classical rules of certainty. They live in superposition, capable of existing in multiple states until measured. Harness this principle, and you unlock astonishing power. A digital computer solving a complex problem must labor step by step, testing one path at a time. A quantum computer, by contrast, explores countless paths simultaneously, evaluating them all at once. For problems of chemistry, biology, or cryptography, the difference is not speed, it is possibility. Digital computers could take centuries to solve tasks that quantum computers may resolve in seconds. The implications are staggering. In agriculture, quantum computers may help design the next green revolution, enabling scientists to replicate the natural process by which certain plants pull nitrogen from the air to create fertilizer. Feeding a growing global population could depend on such breakthroughs. In energy, they could be the key to unlocking fusion power, the dream of limitless clean energy drawn from seawater. The equations needed to stabilize plasma and control fusion reactions are brutally complex. Only quantum computing has the potential to tame them. In medicine, the promise is just as profound. Today, drugs are developed through trial and error, with thousands of compounds tested slowly and often wastefully. Quantum computers could simulate diseases at the molecular level, allowing treatments to be designed within a machine rather than a laboratory dish. Diseases that now defy understanding, cancer, Alzheimer's, Parkinson's, could one day be modeled, predicted, and conquered through quantum simulation. And yet, the stakes are not only about health and energy. Security itself is on the line. Quantum computers, in principle, could crack the codes that protect every piece of digital information on Earth. Banks, governments, militaries all rely on encryption, built on the difficulty of factoring enormous numbers. For digital computers, factoring such numbers could take centuries. For a quantum computer, it may take moments. The anxiety this produces among intelligence agencies is obvious. The race is no longer academic. It is strategic. That is why the world's biggest names are investing in the field. Google, IBM, and other giants are pouring billions into the technology. Startups appear almost overnight and grow into billion-dollar enterprises. Wall Street circles with anticipation. Governments treat it as a matter of national importance. To sit out the race is to risk irrelevance in the future. Kaku describes this moment as the dawn of a second revolution in computation. The first was digital, and it reshaped the world. The second will be quantum, and it may redefine it entirely. To him, digital computers are destined to look like abacuses in a museum, clever, useful in their time, but hopelessly outclassed by what comes next. It is a dramatic vision, but history suggests he may be right. Every leap in computing has rewritten the rules of society. This one may rewrite the rules of reality itself. If quantum computing promises to transform the future, its roots lie in a long human struggle to calculate and to understand. Our ancestors began with the simplest tools, bones and sticks scratched with marks, tallying livestock and grain. For thousands of years, these crude analog methods were enough to count and to trade. Then came machines of gears and levers, culminating in Charles Babbage's designs in the 19th century. His analytical engine, though never fully completed, was astonishing for its time. It could process instructions, calculate interest rates, and even aid in navigation. But Babbage's machine was only the beginning. In the shadows of history stood Ada Lovelace, who recognized that such a device would require not just mechanical parts, but instructions, a program. Her notes on Babbage's machine made her the first programmer in history. She saw what others did not. Machines could follow logic, and logic could be expanded beyond numbers to ideas. The 20th century brought the crucible of war. When Nazi Germany developed unbreakable codes, the Allies turned to mathematics. At Bletchley Park, Alan Turing built machines capable of deciphering the German Enigma system. His work helped to end the war, saving countless lives. Yet his contribution went far beyond military victory. Turing laid the foundations of the modern digital computer. His Turing machine was not just a physical device, but a profound insight. Any process of logic could be reduced to a series of simple operations, zeros and ones. Every computer we know today, from laptops to smartphones, is a descendant of Turing's vision. But history was cruel. Despite his genius, Turing was persecuted for his sexuality. He was arrested, humiliated, and subjected to chemical treatments that destroyed his body and mind. In 1954, he died by his own hand, a half-eaten apple at his side. Only decades later did the world begin to recognize him as one of the true fathers of the modern age. To this day, the glowing apple on millions of devices is sometimes seen as a quiet homage to his tragic life. While Turing gave us the digital computer, Richard Feynman, a Nobel laureate and playful trickster, pointed toward what would come next. He famously asked, "How small can we make a transistor?" Transistors, the switches of digital circuits, could in theory shrink until they were the size of atoms. And if that were so, Feynman realized, why stop there? Why not compute directly with atoms? He argued that nature itself was quantum mechanical. And only by using quantum rules could we simulate the deepest truths of physics. It was Feynman who first proposed the idea of a quantum computer. The difference between digital and quantum thinking is not abstract, it is profound. Imagine a mouse exploring a maze. A digital computer must trace every possible path, one after another, left or right, step by step. The process is long and tedious. A quantum computer, however, evaluates every possible path simultaneously, as if countless universes of outcomes were explored at once. The mouse's journey is no longer a slow search, but an instant unfolding of possibilities. This is the strange power of quantum mechanics. Particles are not confined to one state, but exist in superpositions. Schrödinger's famous thought experiment captured this paradox. A cat inside a sealed box, linked to a device that may or may not release poison. Until the box is opened, the cat is both alive and dead. As absurd as it sounds, this duality reflects the true behavior of electrons and atoms. Quantum computers exploit this reality. Each qubit is like Schrödinger's cat, existing in multiple states until measured. By linking many qubits together, a quantum computer can process a vast array of outcomes in parallel. The result is a kind of computation that feels almost supernatural. Yet this power comes with fragility. Quantum states are delicate. The slightest vibration, a hint of heat, or a stray magnetic field can collapse them, destroying the calculation. Physicists call this problem decoherence, and it is the greatest obstacle to building large-scale quantum machines. To preserve coherence, laboratories cool their systems to near absolute zero, suspending atoms in carefully shielded environments. It is as if the entire universe must be silenced, so the faint music of quantum mechanics can be heard. Remarkably, nature itself has already solved this challenge. Photosynthesis, the process by which plants capture sunlight, relies on quantum coherence at room temperature. The leaf of a plant performs calculations with elegance that no human-built machine can yet match. Mother Nature is, as Kaku reminds us, still far ahead of us in her mastery of quantum rules. As researchers struggle to harness these principles, one truth becomes clear. Quantum computing is no longer speculation. Prototypes exist. Experiments are performed daily. Even cloud platforms now allow anyone to connect to small quantum processors. What was once a dream has become reality. And so the story of human computation stretches from tally marks on bones to machines of gears, from Turing's logic to Feynman's visions, and now to the shimmering frontier of quantum mechanics. At each step, the boundary between imagination and reality has shifted. The question is no longer whether quantum computers will exist. They already do. The question is how they will change us and whether we are prepared for what they will reveal. Quantum computing is not simply a matter of theory. It is about reshaping the foundations of our civilization. When Michio Kaku speaks of their potential, he does not begin with abstract puzzles, but with the most basic needs of humanity: food, energy, health, and security. Consider agriculture. For decades, the Green Revolution allowed us to feed billions through the use of chemical fertilizers. Yet, the process by which fertilizer is produced, extracting nitrogen from the air and converting it into ammonia, remains crude and energy-intensive. Nature performs this miracle with ease, as bacteria in the soil effortlessly bind nitrogen. Quantum computers may help us understand and replicate that process, unlocking a second green revolution capable of sustaining our growing population without exhausting the planet. Energy presents an even greater challenge. Fossil fuels, relics of dead plants and animals, are finite and destructive. Nuclear fission produces power but also leaves behind dangerous waste. Fusion power, by contrast, promises almost limitless energy, with no carbon emissions, no meltdown risks, and no radioactive waste. Its fuel is hydrogen, drawn from ordinary seawater. A single glass of water contains enough potential hydrogen to power a city. But the conditions required to sustain fusion are unimaginably delicate, involving plasma hotter than the core of the sun. To stabilize that plasma may demand the immense processing power of quantum computers, capable of simulating atomic behavior and preventing catastrophic instabilities. If successful, humanity would have access to virtually free energy for millennia. Medicine, too, is on the brink of transformation. Today, new drugs are developed through trial and error. Scientists create thousands of molecules, test them one by one in petri dishes, and hope that one will interact with a disease. It is slow, costly, and uncertain. Quantum computing offers a different path, modeling diseases at the molecular level, simulating interactions within the memory of a computer. Instead of pouring chemicals into glass vials, we could experiment with proteins and DNA inside a quantum machine. This would not only accelerate discovery, but allow personalized medicine, treatments tailored to the unique genetic structure of each individual. But with possibility comes danger. One of the most unsettling powers of quantum computing lies in cryptography. Nearly all digital communication, financial transactions, military secrets, even private emails, is secured through codes that rely on the difficulty of factoring enormous numbers. A classical computer might take centuries to break a 50-digit key. A sufficiently advanced quantum computer could, in principle, do it in seconds. The implications are staggering. Every bank account, every state secret, every encrypted message could be exposed. That is why intelligence agencies, from the CIA to the NSA, are investing heavily in quantum research. The arms race is not only about missiles or satellites, but about who controls the mathematics of the quantum world. This sense of urgency has transformed quantum computing into big business. Tech giants like Google, IBM, and Microsoft pour billions into laboratories. Startups, once obscure, have become billion-dollar enterprises almost overnight. Wall Street has joined the frenzy, chasing what could be the next industrial revolution. Kaku warns that if nations or companies fail to adapt, they risk irrelevance. Silicon Valley itself, once the engine of digital innovation, could become a relic if it does not master the quantum leap. Underlying this revolution is the collapse of a principle we once took for granted: Moore's Law. For decades, computer power doubled roughly every 18 months. Each holiday season, consumers expected faster, smaller, and cheaper devices. That exponential growth fueled the global economy. But as transistors shrink to the scale of mere atoms, strange effects appear. Electrons begin to tunnel through barriers, creating short circuits. At 5 atoms across, the laws of classical electronics simply break down. In other words, Moore's Law is dying. The digital age, miraculous as it was, is approaching a wall. Quantum computers offer a way forward, not by squeezing more transistors onto silicon chips, but by abandoning the binary system altogether. They operate on qubits, which are not limited to zeros and ones but exist in superpositions of states, where a digital machine plods step by step. A quantum machine explores countless outcomes simultaneously. The difference is not speed in the usual sense. It is a new form of computation altogether, one that mirrors the parallel richness of nature itself. The race is global. China, the United States, Europe, all are vying for dominance in what some call the quantum supremacy contest. Unlike the nuclear arms race of the 20th century, this contest is not merely about weapons, but about control of the next economy, the next medicine, the next source of energy. Whoever masters quantum computing may shape the course of the 21st century. And yet, Kaku reminds us, this is not only a race of nations, it is a race against time. Climate change, disease, and economic instability are accelerating. The tools we have built so far are reaching their limits. The quantum revolution is not a luxury. It may be a necessity for survival. For Michio Kaku, quantum computers are not just powerful machines. They are keys, perhaps the very keys, that may unlock Einstein's unfinished dream, a theory of everything. The vision of a single equation, concise enough to fit on a sheet of paper, yet vast enough to explain galaxies, black holes, atoms, and life itself. This dream has guided physics for more than a century. Einstein pursued it relentlessly, but the complexity of the universe resisted him. Today, the leading candidate is string theory, the notion that the fundamental building blocks of reality are not particles but tiny vibrating strings. Each vibration produces a different note, a different particle, and together they compose the symphony of existence. Electrons, protons, quarks, all are simply harmonies played on these strings. Physics becomes music. Chemistry, the melody of strings colliding. And the universe itself, a grand cosmic symphony resonating across dimensions beyond our perception. But string theory is not simple. Its equations stretch beyond the ability of human minds, and even our greatest supercomputers falter under their weight. To test it, to prove or disprove it, requires the power to simulate entire universes of mathematics. This is why Kaku believes quantum computers may be indispensable. By calculating on atoms themselves, by using the strangeness of quantum mechanics to process infinite possibilities, they may one day reveal whether string theory truly is the long-sought theory of everything. It is here that physics touches philosophy. If we succeed, if we find that elusive equation, what will it mean? Will we, as Einstein suggested, be reading the mind of God? Or will the answer be as simple and anticlimactic as the fictional 42 in Douglas Adams's novel? Science, after all, is not obligated to satisfy our sense of wonder. Yet the pursuit itself, the act of seeking coherence in the chaos of the cosmos, remains one of humanity's noblest endeavors. Beyond string theory lies another haunting question. Are we living in a simulation? Films like The Matrix captured the imagination by suggesting that reality itself could be a computer program. The idea is ancient, echoing the age-old suspicion that the world may be a dream or an illusion. But Kaku and many physicists argue that such a simulation is nearly impossible. To simulate even the atoms in a single room requires a staggering amount of information, beyond the reach of any conceivable machine. Quantum mechanics adds another barrier. Atoms exist in countless possible states, until observed. To simulate them all would require simulating infinite universes. The mathematics collapses under its own weight. Yet the idea of parallel universes persists, and not just in fiction. In quantum mechanics, particles exist in superpositions, alive and dead, here and there, all at once, until observed. Schrödinger's famous cat, both dead and alive inside its box, symbolizes this strangeness. Quantum computers, by harnessing this principle, compute across these parallel realities. What sounds like fantasy is, in fact, the engine of the next revolution in science. The same imagination that gave birth to quantum theory also pushes us to consider life beyond Earth. If intelligent civilizations exist, how advanced might they be? Kaku invokes the Kardashev scale. Type 1. Civilizations harness the energy of a planet. Type 2. The power of their star. And Type 3. The resources of an entire galaxy. Humanity, by this measure, is still type 0, burning dead plants for fuel. Yet, in the distant future, with quantum technologies and cosmic engineering, we may rise. To encounter a civilization 100,000 years more advanced would be like ants meeting humans. We would not even share the same scale of comprehension. And so, the journey continues. From the unfinished manuscript on Einstein's desk to the laboratories building fragile quantum machines, the thread of curiosity remains unbroken. The child who once wondered about a mysterious book has grown into a physicist, standing on the edge of a new era, carrying forward a vision that belongs not to one man, but to all humanity. The questions remain vast. Will quantum computers solve the mysteries of string theory? Will they help us cure diseases, harness the energy of stars, or glimpse other universes? Or will they, like every human invention, reveal answers we did not expect? Whatever the outcome, one truth endures. To seek knowledge is to honor the wonder of existence itself. And as long as there are minds willing to imagine, to calculate, and to dream, the search for the ultimate truth will go on. So let us continue to explore, to ask, and to listen to the echoes of great minds who came before us. For in their questions and in our pursuit of answers lies the story of what it means to be human.